Video, we looked at centroids, which is finding kind of that sweet spot where you could balance a shape on your finger if you wanted to think about it that ways. And now we're going to talk about moment of inertia. A moment of inertia is the stiffness that a system provides. It's kind of like, if you want to think about a nice visual, if I have a 2x4, so here's my 2x4, something like that. Am I going to put it in the joist this way, where we're walking up here? Or am I going to lay it flat? Like so, where I walk up here. Okay, what is the difference? They're both the same 2x4. They both have the same material properties. They both have the same dimensions. But the orientation, when I'm looking at bending, if I look, here's my beam, and I'm standing on top, and here's my beam, and I'm standing on top, the orientation of the area is how we get that increase in stiffness by flipping it flat up onto its side. Okay, so let's just go back and look at our little sheet here, and we're going to look at the moment of inertia of just a 2x4. We'll just do a 2x8 because it'll make the numbers even bigger. And let's look at the moment of inertia when we're about this axis. So if these are my reactions and I'm loading on top, I'm bending about this x-axis. And here, I need to make sure that I'm paying attention to which axis I'm taking it about. And right now we're just going to make this flat, and we're going to make this flat so that we can just look at the x-axis. Okay, so here is x. And x-axis is not the length, but it's the cross section when I look at the cross section. Okay, so for a rectangle, it's bh cubed over 12. So if I have my 2x8 in this orientation, then I have I sub x is bh cubed over 12. So I have 8. Okay, the height is 2 cubed over 12. And I get a pretty small number. 8, enter, 2, enter, 3 times 12 divided by. I get a moment of inertia of 5.33. Now, if I come back up here, I'm still looking at the same shape. Okay, so I'm looking at bending. So bending. So now I've got a 2x8. If I want to find that moment of inertia of bh cubed over 12, now I've got 2 times 8 cubed over 12. So let's get that number. So I have 8 cubed, 2 times 12 divided by, and I get 85.3. Okay, so it's the same material, it's the same cross-sectional area, it's the same length, it's the same everything, but that orientation that I put it in determines. That's what makes like a T-beam so very effective, is that we are increasing this BH cubed, and when we build a T-beam, the centroid is somewhere around here. I also remember that AD squared term. So when I talk about the moment of inertia and we look at these equations, and I say the moment of inertia is BH cubed over 12 for a rectangle, then I'm talking about it's about its own centroid. This equation is valid about its own centroid. For the circle, it's the same thing. For a triangle, again, it's the same thing. This is about the triangle's own centroid. When we look at the quarter circle and the semicircle, we've simplified this. This is what you're going to want to use, this x prime and x prime y prime. It is about the centroidal axis, okay? Not about this x or y global, but again, the centroid, which we did last time. So the object is to get this centroid as far away from the centroid of the whole, and that's where we get that AD squared term. So we've talked about this. So now let's look at just a T. If I have a 1/10 and I have a 1/10, well, if I just want to look at this one, okay, BH cubed over 12, I'm going to get 10 So I'm going to get 10 over 12, which is 0.833. So that's not a very large moment of inertia. If I look at this one, I have B, H cubed over 12. So we can already see just by orientation, we are going to get a much larger moment of inertia. So we have 83.33. Okay. Now, what happens when I put these two together and I make a T-beam? Well, the first thing I'm going to have to do is I'm going to have to walk it up and figure out where that centroid is. So we have our chart, A, Y, A, D, Y, and we're going to start with global. I don't know where the centroid is, but I need to find Y bar. Okay, so I have an area of 10. I have a Y from my global to the centroid here is 10 over 2 is 5. So we've got 50. And then I've got this area. It is also 10. This time I've got to remember to walk up 10 just to get to that top piece. And then a half to get to the centroid of that top piece. I have 10.5. 105. So if I add my areas, I get 20. If I add this, I get 155. So Y bar is ADY divided by A. So I have 155 divided by 20, and I get 7.75 inches. Okay, so I now know that this is 7.75 inches. So I'm going to redraw this just a little bit bigger so we can talk about the distances that we need when we start finding that moment of inertia. Okay, so I know that this is 7.75 units up. This is 1. This is 10. This is 1. This is 10. I know the centroid, I'll get a different color so you guys can see this. The centroid of this is going to be right there in the middle, and the centroid one down here is, again, right in the middle. So to find the moment of inertia of a compound system, it's going to be the sum of moment of inertias plus AD y squared. So I'm going to set up my chart again, I sub x. And then, well, I need that area, and luckily, I already have those values up here. And then I need this dy. We'll talk about that in a minute. And then ADY squared. Okay, so the moment of inertia of this bottom piece, when I find Ix, I'm just talking about the singular, the moment of inertia about itself. 1b h cubed over 12, and we already found that right here. Okay, now I need to find the moment of inertia of this top piece about itself, pretending it's singular, 0.833. We already found those areas. Now, this y, when I'm finding the centroid, is going from my global axis to the local axis of each individual piece. Okay, if this is 10 inches, then it's 5 inches from global to the centroid. It's 10 plus 0.5 inches to the centroid. That is from global to each centroid. This dy, this is the distance between our centroidal axis and each piece axis. Okay, so the easiest way for me to do this, let me find another pen here, do a different color, is dy for this bottom piece. Okay, it's the distance from, that's still the same color, let's do red. That's the distance from the centroidal axis to the centroid of my system. And the easiest way for me to do this is I know that it is from global to centroid of the system is 7.75. minus, I know from global to centroid of piece, it is 5, okay, which is the number that I have right here. 7.75 minus 5 is the distance in between. Okay, again, I need to go from the centroidal piece of the hole. Okay, so again, the easiest way for me to do this is, well, I know this distance. That is 7.75. That's my y bar. 7.75 minus. I also know that from the same global x-axis, I can go up, and that's 10.5. So if I want this little nugget right here, it's just this and this, the difference. And it doesn't matter if I get a negative value because we're squaring it anyways. Minus 2.75. That doesn't seem right. 10.5, 7.75 minus, nope, okay. So this is 2.75. Clearly didn't draw to scale, okay? So that's how I deal with the dy. I'm going to take my y bar and I'm going to subtract my y that I found in the centroidal chart. Y bar minus y in the centroidal chart, and you'll always get the right answer. But it's the difference between, okay, the centroid of the whole to the centroid of individual pieces. Now, when I say a dy squared, it's literally a dy squared. It is not this whole thing. So I'm going to take 10 times 2.75 squared, and here I have 10 times 2.75 squared. And I get 75.625 and 75.625. And so the important columns are clearly the moment of inertia of the individual. And if we add this up, we don't get much more than about 84. When I put these two individual 1x10s together into a system, I now get to add this additional 151.25. So now as a system, 235.25 is my moment of inertia, okay? So by taking these two 1x10s, oriented one up, one flat, with a moment of inertia individually of 84, when I put this together and make this composite, maybe I've got a nail in there and I've made it like it's just one shape now, I've really increased that capacity with this ADY squared term. So that's the beauty of in steel. The beauty of a W section is that you can decrease the weight, the self weight of a steel beam, for instance, by getting rid of all of this, but you're getting a very high moment of inertia because we are taking the centroidal areas, okay, and we are squaring that distance, and it's really increasing our capacity. So really start thinking about the orientation of your structure or members in the structure, or if you're putting pieces together to make a cross section, think about how you can orient your system so that you are maximizing the area that you do have.